This is about the last topic on arrays, and it's not about arrays at all. It's about a replacement for arrays called the vector class. And in my last lecture in Java, Vincent and Tu sat through me showing array lists, which are more flexible than arrays. What do I mean flexible? When you allocate an array, you have to allocate it to the maximum size that you want, or else it becomes a real problem when you want to add items past the end of the array. You have to create a new array, copy all the elements in, and then you can put your new elements in there. Or if you want to delete an element from the first entry in an array, what do you got to do? You got to copy element 2 and element 1, and element 3 and element 2 and element 4 and element 3, and so on. You've got to copy the entire array, moving them back one. Or what if you want to insert something into position 5? Well, you copy all the elements up to 5, you put your new value in there, and then you got to copy all the rest of them after that. You can see that, each time you do this, you have to allocate, and you have to do a bunch of copying and stuff like that. So arrays are real cool, but they're not easy to use if you're going to be inserting or appending or deleting from it. If you're just going to fill it up with data from beginning to end, that's awesome. But if you're going to be trying to do something more sophisticated than that, you need a data structure which supports that. You need a class that supports that. And the C++ class of renown for doing that is called a vector. And there are others. The idea of a vector is something that's based on what's known as a linked list. What is a linked list? A linked list predates C++ considerably. It goes back to the 60s or 50s or something like that. For object-oriented programming, but it became far easier to implement with object-oriented programming. The idea is what if I'm going to insert the name Fred into my list? Well, my list starts off empty. Okay, cool. So I create a node called Fred, and then everything in my list not only has a value, but it has a value, and then a next indicator telling where the next item in the list is. And I'm just going to number these, 0, 1, 2, 3, 4, although these will probably really be memory addresses, hexadecimal memory addresses or something like that. All right, now I'm going to insert another value, Greg. This will probably hold a -1 indicating that there is no next value. That's the end of the list. Okay, so it goes. Fred. Well, Fred is not in the list. It's greater than this one, so I'm going to write it here, and then I'm going to update this list. Now, his next is that one. And his next, well, there's no next. And now I'm going to add yet another one. I want to add Bob to it. Is Bob in the list? Well, we start at the beginning. We go to item 1. No, Bob's not there. We hit -1. We know, no, there is no Bob whatsoever. So we get a new element. We put it there. Bob is element number 2, or at address 2. So we fill in our next pointer with 2. And now -1, right, like that. So it's a dynamic list. It expands as we add data elements to it. And we can delete from it pretty easily too. Like, what if we want to delete Greg? Well, we start at the beginning somewhere. There's a counter, not a counter, there's a pointer that says what our starting position is, or 0 address. And we start at the beginning. We're looking for Greg to delete. Is that Greg? No, okay. Well, let's go to the next item. Is that Greg? Yeah, it sure is. So what we've got to do, what's the next item after Greg? 2. Well, I'm going to do that. I'm going to write that his next one is 2. Now nothing points to Greg. Conceivably, you could erase that. You could free the memory or whatever. Right? And then what if we wanted to delete element 0? So we start looking for Fred. Our start is 0. Huh? find Fred? Yeah, boom, right off the bat. Okay, and then our next counter is 2. Okay, well, what do we do? Now, from now on, our start is 2. We erase that, and then next time we traverse the list, we're going to start at element 2. That's a linked list. Now, if you want to maintain a sorted list, sorting with a linked list, you can do that. I didn't illustrate it, but you can do that. Let's see if I can rewind back to where I was. I don't know. I had Fred, and let's have another one. Let's have John. His next item, well, our start is 0. His next item is 1. His next item is -1 to indicate that he's at the end. Now we want to insert Greg. Okay, are you Greg? No, wait, we're not looking. We're looking to find a good place to insert it. So by whatever algorithm we're looking for. Greg, all right. Is Greg greater than Fred? Yeah, it is. We better keep going. Go to that item. Is Greg greater than John? No, it's not. It comes before John. So we're going to create a new element in our list. Well, what's our next one now? 2. And then that 1 that we had, it's copied down to here. So when we traverse the list next time to print it out or do something, we start at 0, we go here, we get Fred, then we go to the next item, we jump down and get Greg, and then we go to the next item, we go there, right? So it maintains itself in sorted order by dint of maintaining this next pointer accurately. Is it the most efficient structure? No. There are tree structures which support far faster inserts to keep your data sorted. And I'm not going to draw how a tree works. But you know what you do is you have a top node. Are you greater or less than? No. Are you greater or less than? No. You know, and you wander down a tree, and you can traverse the tree in sorted order, but it's faster than doing a insertion into a linked list where you just have to start at the beginning and go all the way to the end of the list to find out whether it exists or not. You might get lucky and find it, you know, halfway down, which is great, but otherwise, you know, if your list is 100 items long, to validate that it's not in there, you would have to search all 100 of them. But a linked list is a way to keep your data sorted. And it's also a way to create a dynamic data structure that grows and shrinks as you insert or remove data from it. Like I said, it's not the most efficient. One better tactic is something called a doubly linked list, double linked list, where you have not only a next pointer, but you have a previous pointer. It just makes it easier to, you know, update things if you're going to insert or remove, if you have both those pieces of information when you're sitting on a particular node. Now, vectors are probably implemented underneath it all as a tree, since the trees are more efficient than linked lists, but at the very least, it would be implemented as a linked list. Let's Google that up. Is a C++ vector a tree or a list? What is the underlying data structure of an STL list? Implementation is defined, but generally it's a dynamically allocated array. So it would still have next and previous pointers, but it's stored as an array underneath it. That's interesting. Oh, that's because vectors don't maintain a sorted order. They don't need to, so all they need to do is just, you know, keep adding things to the end, just like a normal array. So, the STL vector is a data type defined in the standard template library. Typically what happens is that people come up with a data structure, and then the next time all the gurus get together and vote on creating, you know, a new standard, then that structure is, you know, request for comments, RFC'd, and people vote on it and they modify it and eventually it becomes part of the standard library. It can hold values of any type. You can have a vector of ints, you can have a vector of floats, of doubles, of bools, If you've defined your own structures, you can have a vector of your own structures. And it automatically adds more space as needed. No need to determine the size of the definition. And what's kind of cool is that you can still use the square braces to access it. You know, if you've added 3 items to the vector, you could use vector name subscript 2 to get to that 3rd item. Why do I say it? That's kind of cool? You can't do that in Java. That's because C++ supports something known, and I hope I don't get the term for this, operator overloading, where you can define what happens if you call the plus sign on a class, on an object, or whether you use a minus sign, or whether you use plus plus, and in this case, or whether you use square braces. C++ supports that operator overloading. And I'm wondering if it's overload or override. I should Google that up. I can't believe I forgot it. But Java does not. So in Java, you have a method for getting the data out of a list, out of a vector, like .get. In parentheses, you provide the number. It's nice to be able to have this syntax, though, be the same, regardless of whether you're using arrays or vectors. Then there's no mental gymnastics required to figure out how to get a piece of data out. You just know you're going to use square braces. So to declare a vector, you have to have an include. Then we can declare our vector. Notice these angle braces. This is what's known as a template. Vector is a template, and it supports any different data type that you want to stick in it, right there. So that declares a vector, which is like an array of ints. You can also tell it how many initial items to start off with. That just kind of improves efficiency. If you know you're going to be adding, not too many items to it, but, maybe up to 30, you go ahead and say, well, go ahead and give me a vector that's 30 items long, and that way as you're appending items to it, you never have to go and grab any new memory. But once you try to add item 31 to it, it's got to allocate new memory, right, to stick on the end of it. Otherwise, though, it's allocating memory every time you add to it. Now, it's very likely that when you declare an array, it's got some pre-allocated, for 5 values or something like that, 5 spots in it, just so that it doesn't, you can start adding to it and it won't immediately have to grab more memory. But, otherwise, as you add items to it, it keeps having to allocate memory for it. If you know you're going to be adding 1,000 elements to your vector, you may as well go ahead and pre-allocate it out to 1,000. If you have no idea how much data you're going to be adding to it, don't preset it with a specific size, right? Just let it grow to the size that's needed. You don't want to allocate it out to 1,000 if you're only going to be holding 17 values. When you're declaring it, you can declare not only the initial size, but what values to initialize it with. This will create 30 values and set them all to 0. And this would create a vector, and we pass in another vector, and it copies all the values that it scores into our new vector. So if you're using C++ 11, invented in 2011, you can initialize a vector the same way as you initialize an array, except you don't use the equal sign. You don't say vector int numbers equals. Otherwise, the syntax is the same, right? You use the curly braces and you list your values there. If you want to append a value to it, you do .push_back. Now, I wish it wasn't that silly of a term. I guess it's just silly to me because I don't program in C++ as often as I've programmed in other languages, where if you want to add an item to a list, you call .add, right, or .append, pushback. All right. Anyways, that puts an item on the end of the array. If you want to find out how many elements are in the array, you call .size. If you've added 10 elements to the array and you call .size, that'll return 10. Now that makes me wonder about what if you declare an array of initial size 30 and then you call .size. Is it going to say 30? Yeah. Maybe so. And then you use pop back to remove the last element from the vector. So pushback pins it, and pop back takes the last element off. At this point, a vector is behaving like another data structure known as a stack. And the way a stack works is just like a stack of paper. If I add, 3 items, I add Eric and Jeff and Doug, and then later on I want to get a value out of it, I go and pop that one off. I got Doug. And then I'm going to get the next piece, that's Eric. And then I'm going to get the last piece, and that's Jeff, right? And so they came in reverse order, right? Last in, first out. The last piece of paper that was put on here, Doug, is the first one that I take out. And that's called pushing and popping. I push something onto the stack, push something else, I push something else, and then when I want to get something, I pop it off the stack, and I pop it off the stack. And so the vector can be treated as though it were a stack with push back and pop back. However, it's got other ways of adding data to it as well, so that you don't always just add things to the back of it. Let's Google up C++ vector methods. See if we can find a list of methods for it. Assign. You want to assign a value, right? I want element 3 to have the word George in it. Push back, add it to the end. Pop back, remove it from the end. Insert, put it anywhere, not just at the end. Erase. I would assume that that's like delete, right? I want element 9 to go away, so I'm going to call erase. Swap. Swap 2 values. Clear. I guess that would reset it to 0. I'd have to click on that to see what it's going to do. Removes all, it doesn't just remove one element. Clear wipes it out, like erases the array, the vector. Suddenly it's all gone. We're going to need to play with some of these. If you're going to iterate through an array, strongly suggest you just use a range-based for loop for each value in the numbers vector. I'm sorry, I keep saying array. For each value in the vector, print it out. For int val colon numbers, print out val. Just like we were doing with arrays. Exact same syntax. Makes it real easy to use. But you could also use a for loop. I mean a for index loop, right? For I equals 0, I is less than vector.size, I++. That would print it out the same way. And here's our methods. There's some cool ones. There's reverse. That swaps, reverses the order of it. Resize. If you want to add elements to your array at the end, you can resize it. Swap. Swap 2 elements of the array. Capacity. Tell me how much room is left, and I keep saying array, I'm sorry. Tell me how much room is left in my vector without allocating more memory. And then at. At tells me the value at that specific element number, at that specific index. So this would return, if I was equal to 2, it would return the element at position 2 from the vector. Or you can just, as of C 2011, just use the square bracket nomenclature like this. Right. That would do the same thing and make it look more like an array. That's what I would do just because it's nice and easy to type.
Can you kind of explain, just like give a brief, like vector versus array? Because I don't really understand the difference.
The vector grows and shrinks as you add and remove items from it.
So why would you ever use it like an array if you could?
It's faster to access. I wouldn't unless I had to.
Okay.
The times that you want to use an array is if your code needs to rip through the array at maximal speed, like you're writing a video game or something like that. Because if you're traversing a linked list or a vector or something like that, then the items are not necessarily all contiguous in RAM. And so these items may be here, and then these items may be here. And so searching them, require, if your chip asks for a memory address, it can get a range of values. But you know, if it's stored here in this megabyte as opposed to this megabyte, it's not going to read all of that stuff just to get, you know, those two values. So it's going to ask one at a time for them. But if it's an array, you know, get this block, and then you know that every 4 bytes is another int in that, and so you could rip through it really fast.
Do other languages use strictly vectors and call them? Because I feel like in other languages,
Python only uses vectors, although they
What
call
they
them
call them,
lists.
right? Oh.
Right. Java supports both. Some languages support both. Some of them completely do away with the idea of arrays whatsoever. Why might you want to do that? Just, I don't know, make it safe, right? You know, you can't, no, I can't say that. I have no idea why Python didn't support arrays. It'd be worth, you know, Googling it up. But Java supports both. A lot of languages support both. They have kind of, you know, arrays as the primitive, more primitive data type, and then they have the cooler data structures.
And so like these have different syntax because like you can make that vector look like a lot like an array.
In C++, the syntax looks a lot, very, very, very similar. Other languages don't support operator overriding to where you could use the square brackets in order to get the elements out.
Okay.
Java is one of those languages. Now, Python does let you access it like it was an array.
Yeah.
And as far as Python is concerned, or as far as a Python student is concerned, an array is a list, is an array. They can't tell any difference
That's
between the
kind of
two.
I feel like I've learned that arrays you could do all that stuff with, but now I'm learning that those are actually vectors.
Exactly. Exactly, they're not true arrays. They're not fixed in length.
Okay.
You can insert, you can remove from the, you know. Right, exactly. Very good question.
Do the sorting algorithms like bubble sort work with?
There, I am sure that there are vector sorts. As to what algorithm they use, I doubt it's bubble sort. Bubble sort is easy to code, but it's not by far the most efficient. There are other sorting algorithms that are far more efficient. Let's do vector sort C++. It's an entirely different thing. You want to sort your vector, you call standard : sort, and then you say my vector dot begin, my vector dot end, rather than having it as a method of the vector itself, which strikes me as odd, but I didn't invent them. And I'm sure that the reason they did that is so that this same syntax could be used on any particular, on any dynamic structure, any dynamic template that, you know, can be sorted. So it wouldn't matter whether this is declared as a vector or whatever. std sort would still do it. Our textbook does not get very far into arrays, and they are incredibly useful. If you're going to become a C++ programmer, I would strongly recommend looking up extra stuff on vectors and then trying your hardest to use them over arrays. And then use arrays too, because like I said, they're the fastest, and so if you're optimizing for speed, you would prefer to use arrays. But you don't optimize for speed unless you have to. It's more important that the code be easy to write and easy to maintain than fast. Usually you write your code to be easy to write and easy to maintain, and then you find out there's a performance problem and you go and you correct that. That's an actually good way of doing it. You optimize last rather than first. It sounds stupid, but like I said, if it runs fast enough, you don't want to write code that's more difficult to read. Now, in a particular case of arrays, it's not particularly difficult to read what an array is doing, but I'm talking about like inserting into the middle or whatever. Now, I'm sure that there are libraries for manipulating arrays like that. Let's go ahead and play with a vector. We've actually hit about the last slide, I believe, but we may as well get a little bit of experience adding elements to an array and printing out the array. I'm not going to give you an assignment on vectors though, so this will be the only time you see them until you get a job. But that's not true. If you go to another programming language, then you're going to also be seeing, Java calls them array lists. They don't call them vectors. Python calls them lists. doesn't call them vectors. But still, same exact idea. Underneath it all, they're the same thing. We're in lecture T.
I don't actually know Python, but I was looking it up and somebody said there's a list type you could just use instead.
List is the array type in Python. Exactly.
Hmm.
So it's fun when you're teaching fundamentals of programming and the book is talking about arrays. And if you're teaching it with Python, every 10 minutes you're saying, except in Python, because all the concepts are the same, but then the concepts are different too, because the Python list is the vector class, which is more, far more flexible than a simple array. So the book will say the array is fixed in length, and you go, except in Python. You just have to tell them, learn what the book means, because you'll see that in other languages. And then for half the semester, you treat lists as though they were exactly arrays. You allocate it out to the correct length. Anyways, don't know why I'm babbling about that. Boilerplate. Alrighty. I'm going to steal my code by looking at the sample code here. Let's declare an array of ints. And for you Java guys, notice that in C++ you can declare your vector with lowercase I and t. You can use primitive data types. In Java you cannot. You can only use classes. So you would have to use the wrapper classes like capital I-N-T-E-G-R. Small difference. Let's do that. We're going to need to # include vector. So, # include vector. Now they were demonstrating initializing your vector with values, and I'm not going to do that. Vector, angle, brace, int. I'm going to call it scores. Then I'm going to add some numbers. I could let the user type them in, but whatever. Scores dot push underscore back 100. I'm going to copy and paste that and change the numbers a bit, 90, 95, 91, 99. Alright, let's print them out with a range-based for loop. For int I :scores, cout, arrow, arrow, I, arrow, arrow, quote, space, quote, semicolon. And then after our for loop, let's cout, arrow, arrow, endl. I so wish it would preserve this setting between sessions. Alrighty. So there's my numbers. 190, 95, 91, 99. Each pushback inserted it, or not inserted it, appended it to the end. What if we want to get that last value? I would use a pop back. But instead, I'm going to treat it like it was an array. Int first score equals scores subscript 0. That is valid syntax. More valid syntax. First score equals scores dot at parentheses there. Those are synonymous. C++ supports this because it's awesome. They support operator overriding. A lot of languages don't, and so they have some variant of that. Java, it's .kit. Python also uses the above syntax because it's awesome as well. Java is awesome for its own reasons. Both of these do the same thing. Let's remove that first element. So when we print them out, it's not going to say 100 anymore. Scores dot, oops, delete, erase. Is that how you do it? Getting worried here. Well, that didn't work. Oh, for Pete's sake. All right.
Just push it back to a negative number?
Now they're adding numbers both positive and negative. But if I want to delete the first element of it, let me get that syntax back. Erase. Scores dot erase. Scores dot begin. Plus 0. Now the plus 0 looks stupid, right? You could leave that off, but that's the index number. So if you wanted to delete the second element, you would make it plus 1. If you wanted to delete the third element, you'd use plus 2, and so on. And presumably you could use scores.end and subtract. That'd be my guess. All right, but now I'm going to print it out again, so I'm just going to copy my little for loop here because I want to see that number gone. All right. I never did a second. Apparently, I never did an ENDL. I said I was gonna.
Behind your for loop. Your second one after it, once you scroll down, there's your end.
Oh, there it is. All right. Yeah. Okay. Need to copy that and push it up under the first one as well. There. And there we go. It did, in fact, remove the first item. Now, if I want to get rid of 91, what is his index value? And don't say 3. It is the third element, but what's his index value? 2, right. So I'm going to use the same syntax. And I'm going to delete items begin plus 2. And I think I'll make comments. Index 0. Index 2. Now how about reversing it? Scores dot reverse. I'm not seeing reverse. I thought the PowerPoint slide said that we could reverse. right there. So just not liking that I didn't put them. It's saying it has no member element reverse. The slide is saying that it does. See, Visual Studio is saying it doesn't. Oh, I'm not going to mess with it. Okay, I can't help it. Google reverse C++ vector. You know what it probably is that it's supported in a later version than the version of Visual Studio that we're using. Well, there's standard dot reverse. All right. Apparently we're going to have to go ahead and play with a little bit doing # include algorithms so that we can do the sorting and so that we can do the reversing. So come back up here and do # include algorithm. And then right here, after I push all my data on it, my 100, 90, 95, 91, 99, and so on, I'm just going to reverse it. Now that demonstration on the internet told me to type in std : reverse. However, we have this using namespace std up there, so we don't necessarily have to do that. I could remove the std : So, std reverse scores dot begin parentheses scores dot end parentheses. So now 100 should be the last element rather than the first one. And if you're used to using Java array lists or you're used to using Python lists, then this syntax looks way more complicated than it feels like it needs to be. And since C++ hasn't been my primary bread and butter for about 15 years, it now looks alien to me as well. But not that hard once you see it. And there we go. It sorted it. Can I say that it did? 99, 91, 95, 90, 100. Oh, it just reversed it. It didn't sort it. Derp. Alrighty. So let's sort it and then print it out again. So here, I'm going to skip typing the std : because we have that using std up at the top. So sort parentheses scores dot begin parentheses in parentheses comma scores dot end parentheses in right parentheses in parentheses, and then I'm going to copy and paste my for print loop one more time. There we go. First time is reversed, the second time it's sorted. And then we deleted element 0 at index 0, and so the 90 disappeared, and then we deleted element 2, index 2, and so that 99 disappeared. And we can insert. Let's insert into it. I'm going to save time and just do vector insert C++. Knowing I'm going to have to Google it up anyways. Alrighty. Same way. Alright, so down here at the very bottom, before .pause, I'm going to do scores.insert, parentheses, scores.begin, parentheses, in parentheses, and then the value that I'm going to insert. Bummer, I only made an 80. Then I'm going to print it out. what I would wind up doing if I needed to use vectors is I would wind up writing my own wrapper functions so that I could just call dot append, because I like that name better than pushback. So I can just call insert and not have to use scores.begin, right? What if we wanted it to be the second value rather than the first? I want that 80 to not be the first value, I want it to be the second one. I would put a +1 there after scores.begin. And now that 80 is the second value rather than the first. Like I said, if you're going to become a pro C++ programmer, play with vectors a lot more than what we're doing in here. Sometimes I skip them or not skip them, but give them very, very short shrift if, depending upon where we are in the lecture. I think I've actually skipped them in the past, which is doing the students a disservice. But we're ahead of schedule, actually. I'm pleased with our progress. I can't think of much more to demonstrate about vectors. We know how to iterate them, right? Just like that. We know how to get values out of them, just like arrays.
Could you convert an array to a vector?
Let's find out. You can create a vector to a vector. Let's create an array. Int, no, that's Java. Int nums is equal to 5, 6, 7, 8, 9. Now let's create a new vector. Vector, angle brace, int, in angle brace. I'm going to call it vnums because it's a vector. And I'm going to put parentheses and put nums inside the parentheses. And it doesn't seem to be working. No instance of constructor whatever accepts an array. Well, pooh. Gotta be a way. Google is our friend. Create a vector from an array. We could just write a loop, right? And add each item in the list. Initialize a vector in C++ 5 different ways. I hope one of them is within arrays. Initializing from an array. All right, here's how we do it. Get lost. Oh. You have to specify the array itself and then the length of the array. All right, we can do that. What's the length of our array? It's 5. So nums, comma, nums plus 5. Should I calculate the length of the array? Right? Yeah, I should. Well, I didn't print it out. Let's print it out. So for parentheses int I is equal to 0, I is less than 5, I plus plus. This is lousy. Let me do I is less than vnums dot size, parentheses in parentheses. And this time I am printing out as though it exactly was an array. So cout, arrow, arrow, vnums, subscript, I, subscript endl. Why did I show that to you? Just because you need to see the syntax, not only use range-based for loops all the time, even though they're seductively easy to type. And I certainly would use them all the time as long as I could get away with it. And I want you to see this syntax as well. All right, so hopefully our vector contains 5, 6, 7, 8, 9. Yep. And this plus 5 should really be size of nums divided by size of int. Right, or we should create a variable. Const int nums length equals size of nums divided by size of int. So that instead of saying plus 5, I can do plus nums length. This makes me think that if I wanted to skip the first element, I might be able to say nums plus 1 and just get 6, 7, 8, 9. I don't think that's actually going to work. What do you know? Alrighty. That bugs me.
That works.
I'm not going to try to explain why it bugs me, but it bugs me that that worked. Okay, I'll explain why. I'm passing this in, right? It's probably being passed in as a pointer, actually. And so when I say nums plus 1, to me that would make me think that it thought that the beginning of the array was 6. Oh, well, maybe when I said 5, it just read to the end of the array. What if I do... Instead of plus nums length, what if I just do 3? Is that going to give me 6, 7, and 8? Let's find out. Five, 6, 7. So that would be plus 0, plus 1, plus 2, plus 3, and yeah, so it got me 6, 7, and 8. When in actuality, oh, because I removed my plus 1 from here? I'm getting obsessive. Okay, that's about what I was expecting. Why does it say 6 and 7? Because it's starting at subscript 1, which is that, and it's ending at subscript 3. 0, 1, 2, 3, but that's not 7. Okay, I'm not going to worry about it. But 3 minus 1 is 2, so it's going to start at position 1 and get 2 pieces of data. And so enough of that. I'm going to get rid of that. I'm going to change this back to nums length and consider our lecture over. Vectors to be done. Alright, we have a little bit of time left, so I want to talk about pointers. We've talked about references, but we haven't talked about pointers yet, I do not believe. So, not even looking at any PowerPoints. Pointers are incredibly important. It's just like everything is incredibly important, so how do we know what order to do things first? However, they're dangerous. A lot of languages don't even support the idea of pointers. What is a pointer? It just contains a memory address. And then the program can use that memory address. Well, why is that dangerous? Well, what if the memory address points to some memory that that program does not own? Right? You're not supposed to be reading past memory that you don't own, or writing past memory that you don't own. Usually that results in a program crash. So languages like Java do not support the idea of pointers, which makes them far safer because you're not setting up a situation where it's likely to write past. So anyways, here's what we're going to do. I'm going to declare a variable, int x. I'm going to set it equal to 99 for funsies. And now I'm going to declare a pointer to x. So I'm going to do int star px. The star means this isn't an integer, it's a pointer to an integer. So if I did double d equals 99.9, if I wanted to make a pointer to a double, I would do double star. Now it's just very common nomenclature to put a p in front of the variable name if it's a pointer. That's the reason I did that. Do you have to do that? No, I could call this Fred. Right. But if you have a variable named x, then calling it px would mean pointer to x. If you have a variable called name, then p name would be a pointer to name. Age, p age. Looks like page. Okay, anyways, but it doesn't point to anything yet. It's an uninitialized variable. If we printed it out, it might say null. It might have some random data stored in it. We're going to set that variable equal to the address of x. So px equals ampersand in this language means address. And now I'm going to change that 99 to something else. I'm going to do ampersand px equals 101. And I got it wrong. Is it star px? Yeah, okay. And now I'm going to write out x. C out x, arrow, arrow, ENDL, system pause. Mac users forget the system pause. Just know that everything else we printed. Heck, you can just stick a return there if you want, right? All right, and it printed out 101. If you look at this code, how in the world did x become 101? We never changed the value of x, right? There's no x equals 101 anywhere. But by the time we got to here, x did in fact equal 101. That's because we did it by its pointer. A pointer is an address. I want you to go and paint my house purple. I'm not going to give you my house, I'm going to give you my address, and then you're going to drive over to my house and you're going to paint it purple. This is the syntax for referencing the memory that the pointer points to. If we see out px here, we're going to see an address. If we see out ampersand px, we're going to see the contents of x. So let's do that right here. Let's do two particular couts. Cout, arrow, arrow, quote, px equals, end quote, arrow, arrow, px, arrow, arrow, ENDL. And then do the same thing, copy and paste, except change px to star px on the second print statement. So all I did is I copied, and I'm going to make this star px.
Did you copy a line like that?
Oh, what I do is I go to the beginning of the line, and then I either hit Control-Int. Whoops, no, that's wrong. Now that you've asked me, I've forgotten how to do it. Let's. What I do is I position my cursor at the beginning of the part that I want, and then I hold the Shift key and hit down, and it grabs the entire line.
What, Control, Shift?
Not even Control, just Shift down arrow. Grabs that line.
Huh.
Then you do have to hit Control-C to copy, and Control-V to paste, if you're not going to use the mouse.
Oh, you could even do up to do the above fly.
Yep. Shift up, and you can select multiple lines like that. And let's change this last one. Tell you what, delete that last cout, but copy these and make it say x equals arrow, arrow, x, and then ampersand x equals, and then change that to ampersand x. Whoops, not ampersand xx. There.
Hold on, I'm trying to print that out.
All right. So what we see here is that x has a value in it, 101 or whatever, but the address of the x variable, the data that holds that 101, is that memory address. So byte number 4EF874, and then the next 3 bytes after that all comprise the 4 bytes that hold that int. We set px equal to the address of x. So that's the contents of the pointer variable. But star px gets the data that's stored at that address. Now the reason it's different, 99 to 101, is because I did that between the two.
So regardless of how you change the data inside of it, the address of it is the same for both.
Exactly, right. If I kept changing the value of star px, or if I kept changing the value of x, then the pointer's value is not going to change. because you painted my house purple, but it's at the same address. So why is that important? Well, before the invention of reference parameters, before the invention of C++, pointers were the only way that you could pass data into a function and have that function change the data and pass it back out. Like this. Void change me. And I'm not going to declare an address, an integer. I'm going to declare a pointer to an integer. So it's going to be int star PINT, pointer to an integer. And then I'm going to say star pint is equal to 1,000. Now here I'm going to declare a variable, and then I'm going to call change me on it. Int age is equal to 32. Change me, parentheses, ampersand, age. And then C out, arrow, arrow, quote, age equals, end quote, arrow, arrow, age, arrow, arrow, India. Hopefully I've convinced you before this lecture that if we passed a variable in, that function can't change it unless the parameter is defined as a reference. Well, this is another way to do it. It's the original, it's the old school, original gangster way of doing it. And there we go, age became 1,000. When you see this syntax, when you see star in front of a pointer variable, that's called dereferencing. We dereference, meaning we access the memory at that address. Ought to be called depointer, right? Because we already have a reference type. Okay, let's define another function that uses a reference, just so that we make sure we understand both syntaxes. So this changes it by pointer. Let's write one that changes by reference. Void ref change me. And then the way you declare a reference is with the ampersand. And it becomes kind of confusing. You use ampersands in this place, and you use stars in this place, and then you use ampersand somewhere else, and the C# language cleans some of that up. But, you know, C++ just grows. Things never get removed from it, they just grow. Okay, so int ampersand I. And we're going to say I is equal to 2,000. Does the same thing, effectively. So if we come down here and we call change me and pass age in once more and then print it out, I'm getting an error here and I don't, because it's no longer change me, it's called ref change me. Should have called it change me R, easier to type. Ref change me by reference. We'll see that after that age has been set to 2,000. This syntax, the reference, is preferred just because you can't kill your program by passing in an invalid address. What do I mean by that? When I passed in ampersand AGE as my address, what if I passed in the address of a different kind of variable or something that doesn't exist? Change me, and I'm going to cast it to being a pointer to an int star, in parentheses, and I'm just going to type in a number. Whatever is at memory address 5,000, I want you to change that to this number. Obviously, that's a bad idea. I'm sure that element 5,000 or memory, the 5,000th byte in your computer is not something that this program should be touching. And so it blows up, right? Access violation. So break it and then come up to debug and stop debugging. You see what I mean? Just by passing an invalid pointer.
How could you give it that permission?
Pardon me?
How could you give it that permission?
You can only change data that you're supposed to change. Now I say that. Obviously programs do get away with doing that, which is how, viruses, and things like that wind up
Like if I
gaining
said
control of data that they're not supposed to do. One thing is that it depends upon the privileges of the program. If the program is running at a high enough privilege, then it may be able to write anywhere in memory. I don't know if that's an accurate statement, but you're always hearing about programs trying to obtain root access. Root access on Linux just means that it's the account that can access any file on the machine. I know that in the concept of processors, there are similar ideas where certain processes can have higher priority, which means that they run more often, but also that certain things can have higher access levels. Don't know how to do it though. Feel free to learn how to write a C++ program that will do skullduggery. I don't know how to do it.
So you're saying if I brick a computer, that's fine?
Yeah, I'm not saying none. Alright, so break and stop. Obviously you don't want your program to be killing itself like that. But while we're at it, it might be fun to show what happens if you write past the end of an array. Just because we tend to be curious about things like that. Alright, I'm going to change this back to something valid. Then I'm going to talk about the syntax, and then the last thing we'll do will be just to illustrate writing past the end of an array and seeing what changes. Okay, so the syntax is that since change me, since it got a pointer as a parameter, when we call it, we need to pass in a pointer. We need to pass in an address. Now since we had that x and then px, we could pass in px. Although, it'd have to be down here where after we had declared it and set it right down here. We could do change me parentheses px, and it would work. Why didn't we have to put an ampersand in front of it? Oh, this still would not work because px doesn't have a value yet. All right, there we go. Right, that would work. Why? Because px contains the address of x, just like this argument is the address of age. So you can store that address in a variable, in a pointer variable, and then pass that in, or you can just pass it in directly like that. All right, let's declare 3 arrays. Int nums1 subscript in subscript, or how about just a, b, and c? Int a subscript in subscript is equal to 22, 23, 24. And then int b subscript in subscript is equal to 1, 2, 3, and then int c subscript in subscript is equal to 98, 99, 100. Now let's do this. Change that 1, 2, 3 to something like 21, 31, 32, 33. Just to make it obvious when we print these guys out that the data is going to be different. We're going to need 3 for loops to print those guys out. Range-based for loops are the fastest to write. So for parentheses int I equals 0, I less than 3, I plus plus, C out, A subscript I, followed by a space, arrow, arrow, space. Not A subscript X. I said I just typed X. C out A subscript I, arrow, arrow. I'm going to take those braces out just to save some typing, and then C out on the next line, E and D L. And I'm going to do that for B and C as well. So I'm just going to copy that code, paste it 2 more times, and change the A to B's and to C's. So this is what the arrays look like, those 3 arrays look like before we do what I'm just about to do, which is to overwrite the beginning and the end of the array. So, how about this? Let's change 5 values in a row to -1 or something like that. So for int I equals -1, I is less than, I think I want to go out to 4, so I get -1, 0, 1, 2, 3, yeah. So I equals -1, I is less than 4, I plus plus, and change B subscript I equals 0. Let's just wipe them all out. And then copy and print these, copy and paste those print statements again after our naughty loop here. Why do I say it's naughty? Because if I is equal to -1, it means we're writing before the loop. We're writing before the array. And if I gets up to 4, then we're writing past the end of the array because it's 3. So, alrighty. And there we go. Our array did equal 22, 23, 24, 31, 32, 33, 98, 99, 100. And then it becomes 22, 23, 24, 0, 0, 0, 98, 99, 100. And I'm stymied as to why that happened. It should have corrupted some memory. How's about if we compile it for release mode rather than debug mode? Let's see if that changes its behavior. So I pull this little pull down here. I'm going to build it. And instead of run with the debugger, I'm going to run without the debugger. Start without debugging. Nope, it's still not managing to overwrite the end of the array. Or the beginning of the array. Well, I has a sad. I know we could get it to crash by changing this number to a large enough value, like 1,000. We're just going to start writing past the end of the array, and then we're going to write 1,000 zeros after that. Yeah. I'm going to do something dumb here. Keep running as long as A subscript 2 is equal to its original value, 24. See if that ever, nope. How's about if we do C subscript 2, 0, 1, 2, which is equal to 100. If it ever changes from being 100, we know we've written, that's where we ought to. All right.
Wait, where are you using a C? Oh, no, I don't think so.
Okay, please to repeat the question.
Nothing. No.
I was pretty sure I'd be able to They must be separated fairly far apart in memory. This is the code that I wanted to run our arrays that were declared before and after it. I'm just going to print out the address of those three arrays. So C out, arrow, arrow, quote, arrays, space, end quote, arrow, arrow, A, arrow, arrow, followed by a comma, space, end quote, arrow, arrow, B, followed by a comma, space, followed by arrow, arrow, C, followed by ENDL. Now you may wonder why that's going to print out the address of it. It's because an array is a pointer, actually. In C and C++, an array and a pointer are exactly the same thing. It's weird, but it's true. So that will print out the address. So the difference between that one and this one, EC4, EAC. So my second array actually comes before the first array. And how many bytes apart are they? Well, I don't know. I'd have to check to see what AC minus C4 is. OX C4 minus OX AC. 18 hexadecimal. But since it's 3 ints, I was expecting it to be 12 apart. Instead, they're, what is 18 and OX 18 in decimal? 24. So there is 3 bytes of space between my first two arrays. Meaning that if I go back to -4, I might get to right past the array. So this will be the last effort. I'm going to uncomment this. I'm going to say for I starts at -4, and then keep going while I is less than equal to 3 plus 4, 7. Now I'm hoping that that'll go far enough back and far enough forward without killing the process altogether by writing outside of memory we own. And it did. It did some skullduggery. It wiped out 3 elements of the array before it, which are these last ones, and 2 elements of the array after it. We can get it more precise then. If we make that -3 and we make this less than 6, does that look good? Well, what I'm wanting to get it to do is just to replace the first one and the last one. Well, that didn't do it. Why did I have to go out to -4? All right, we're about done. Sorry, guys. I really wanted to show you writing past the array. I think I have demonstrated that by writing to the B array but with invalid indexes, we were able to destroy data in the array A and the array C. And we did it without it noticing. It did it without generating exception errors, stuff like that. And pointers are the same. Pointers can create silent errors where we're changing data we didn't mean to change, but it doesn't cause the operating system to kill it. So references are far safer. You can't kill your program just by passing in an invalid reference. There is no way to generate an invalid reference. I say that. You'll probably find a way around. No, I'm kidding. All right. So why don't we stop there?
What was that you told me to do? Find a way to
Pass an invalid reference into a C++ reference parameter. Google that up. See if you can find one. Okay. So anyways, let's create a Dropbox for that. I hope the fact that we veered off at the end was okay. I did want you to see corrupting data using writes to an array. That was my big goal. If you compile for debug mode, Microsoft adds little variables on either end of the array, and then it checks the contents of those variables when the program is done to try to detect whether corruption occurred or not. Debug mode goes to a lot of effort to try to capture problems like that. And I kept y'all late.